Nonpolar molecules. Atoms and some molecules do pull on shared electrons with the same force. So here's a nonpolar molecule. We talked last time about polar molecules, which were things like water. And in that case, there are two hydrogens and one oxygen. And hydrogens are little. They only have one proton in their nucleus. So the shared electrons spend more of their time here, which ends up making this side more negative. And since the electrons are not here much and the electrons are negative, this side ends up being more positive. Nonpolar molecules are not like that. These are the shared electrons. So here's one shared electron pair and here's another shared electron pair. And the electron pairs spend equal time on each side because the protons here are exactly the same number as the protons here. They don't pull any harder on the electrons. The electrons are not attracted to one side any more than the other. So it's really very, very even. They spend equal amounts of time. So there's not one positive and one negative side to that. So the electrons don't spend more time on one side of the molecule than the other. They are shared evenly, and there's no funky charge separation. Electrons shared equally between atoms produce nonpolar molecules. So I'm defining that twice, I guess. So here's carbon dioxide, and this is not a bent molecule, and it's because there are these are double bonds. And so anyway, what you need to know is if I show you carbon dioxide and I show you it's this flat molecule, you have to get the idea that this oxygen doesn't pull any harder than that oxygen. And so this ends up being a nonpolar molecule. And students are usually pretty panicky. How can I tell? How can I tell? What I want you to do, for me, is understand that nonpolar are different from polar. And that things that are polar, I'm going to show you in a little bit, will mix with water, and things that are nonpolar, if they're large enough, do not. So that's really the gist of what I want you to get here. So here's another nonpolar molecule. Carbon, carbon, carbon. There are 3 carbons. This is propane, and the rest of the bonds are filled by hydrogen. Does that hydrogen pull any harder on the electrons than that hydrogen? No. This entire molecule is even. This hydrogen doesn't pull the electrons any harder than that one. It's all even, even, even. So this would be another nonpolar molecule. Quiz time. Which side of the water molecule is negative? The electrons spend more time here, and electrons are negative, so that side's more negative. And which side's more positive would be the other side. What do you think a bunch of water molecules would do if they were all together? So hopefully you just watched the video right before this one when I talked about this a little more, but here's the idea when they all get together. The oxygen from one, remember that oxygen is slightly negative, and the hydrogen over here is slightly positive. So this side is going to be attracted to oxygen. And so they're all going to line up that way with the oxygens of one molecule being attracted to the hydrogens of another molecule. So that's the way they will line up. So the next thing that we need to talk about are hydrogen bonds. This is a very weak bond, and it's between the hydrogen of one atom, or sorry, the hydrogen of one molecule and the, it can be any negative part of another molecule, or it could be the same molecule. So the negative part of one polar molecule is attracted to the positive part of another polar molecule. So remember, this is water. The partly negative side here is attracted to the partly positive side here. This positive is attracted to that partially negative. This partial negative is attracted to that partial positive. These really technically should have parentheses around them all, but close enough. This positive is attracted to that negative. So these are hydrogen bonds. Hydrogen bonds may form between two different molecules, like two different molecules of water. And here's what hydrogen bonding, here's another picture of that. So this is showing you the hydrogen bond. So here's what you have to know. This thing is showing shared electrons. That's a covalent bond. Covalent bond. Think of a covalent bond as really strong. Veil, think of a woman getting married wears a veil, or at least they did in the olden days. And especially back in the olden days, marriage was something that you did and you stayed in forever. And so think of this as a really, really, really strong bond. Gee, once you're married, you're married. So these bonds can certainly be broken, but it takes little bit of energy to do that. So this is a very strong bond. These things right here, this is trying to show you, I don't know if this is exactly how you should draw it, but this is showing you a hydrogen bond. This side isn't sharing electrons with this side. It's just that that's sort of positive and that's sort of negative, so they're attracted to each other. Here's just one more picture of water showing the positive side of one being attracted to the negative side of another and how they're all going to line up. Hydrogen bonds are responsible for something called surface tension in water. So if you've ever seen these really cool bugs walk across water, this is how they do it. The water molecules form almost this, I don't know, this skin or something almost across the water. The water molecules on the top are being pulled down by all of the water molecules under them. They're all attracted to each other. And so that gives you a surface tension along the top. Another way that you see this, if you've ever had a cup of water, you're going to pretend I drew that right. Here's the top of the water. If you've ever poured water over it really, really, really carefully, just dripping it in, and the water goes slightly above the cup, that's also surface tension. So here's some hydrogen bonding that's happening between molecules that are not water. So this is some type of an alcohol because it's got an O and an H. And you can see that these are attracted to each other.
I told you, it's different. It's all moving around here.
It's true. Hydrogen bonds may also form between two different parts of the same molecule. So here's a big molecule, and you can see the oxygen in one part of it is attracted to the hydrogen in another. So this might be a really big protein, and the shape of the protein will determine its function. So these intramolecular forces, a force within one molecule, is sometimes really, really important. Hydrogen bonds are very weak. You can put a star next to that or a whole bunch of stars to remember that. So think of covalent, val being, if you can remember that whole wedding thing, very, very strong. Hydrogen bonds are weak because it's just a partial negative attracted to a partial positive. So here's one example where hydrogen bonds come up. We'll do DNA in several months from now. Here is a molecule of DNA, and this is showing the molecule unzipped. Here you have covalent, covalent, everything along here is covalent. But right in the middle, right along here, these are hydrogen bonds. And right along here are also hydrogen bonds. The hydrogen bonds here were just broken, and they're putting in, the enzyme is going to put in new DNA. And so you want to be able to break that bond apart whenever you unzip DNA to replicate it or whenever you use it to read it and make proteins. So it's important to have some kind of weak bond so you can unzip DNA. And the hydrogen bond serves very well for that. So you want a weak bond when you unzip DNA.
I didn't know we could do that.
I know, isn't that cool?